Over 2,000 years ago, the Pythagorean Brotherhood used this geometric figure as a symbol of their identity. This shape became an icon of revolution in the 20th century, even appearing as an emblem on the cap of a revolutionary figure. The flags of dozens of countries incorporate this shape. Various organizations and businesses have also integrated this shape into their branding. The pentagram is one of the most common geometric shapes in human artistic design. Why is the pentagram so captivating? Its appeal lies in its unique geometric structure, embodying symmetry, recursive nesting, and the golden ratio. These features imbue the pentagram with mathematical elegance and visual allure. In this video, we'll delve into the geometric properties of the pentagram and the fascinating mathematics behind it. On a circle, mark 5 points to divide it into 5 equal parts. Connecting adjacent points gives us a regular pentagon. Connecting points with one point in between creates a pentagram. This way of drawing a pentagram has 5 equal-length sides and 5 vertices with identical internal angles. The difference from a regular pentagon is that its sides are allowed to intersect. We generally call such polygons, where sides are allowed to intertwine, star-shaped polygons. Of course, you could look at a pentagram in another way, thinking of it as a non-convex polygon with 10 sides and 10 vertices, but that's not the typical way we perceive a pentagram. The intertwining of sides reveals a complex symmetry and layered effect. Each side seems independent yet interrelated, creating a sense of visual dynamism. This intertwining is fundamental to the pentagram's appeal. Before delving into the geometric properties of intertwining in a flat pentagram, let's first appreciate the stunning allure of a three-dimensional pentagram constructed through intertwining planes. 12 regular pentagons interweave to form a great dodecahedron. In the great dodecahedron, each pentagonal face has a pentagram pattern in relief due to the intertwining with other faces. This three-dimensional intertwined structure gives it a charm far beyond that of an ordinary polyhedron, making it a classic symbol in mathematics and art. Apart from the great dodecahedron, there's also the great icosahedron, small stellate dodecahedron, and great stellate dodecahedron, collectively known as the Kepler-Poinsot polyhedra. The Kepler-Poinsot polyhedra are all constructed through the intertwining of regular polygons. This intertwining introduces complex spatial structures as well as a unique aesthetic. Returning to the flat pentagram, let's examine the geometric characteristics of its intertwining sides. Under mirror symmetry transformation, the pentagram remains unchanged. With rotation at certain angles, the pentagram also stays the same. Though the arrangement of sides differs in terms of symmetry, the pentagram is completely identical to a regular pentagon. Additionally, the intertwining in the pentagram forms a recursively nested structure. At the center of the pentagram is a smaller regular pentagon, in which another pentagram can be drawn, and this nesting can continue indefinitely. The symmetry and recursive nesting structure brought about by intertwining can also be observed in other star polygons. In star-shaped hexagons and heptagons, we can see the same mirror symmetry and rotational symmetry observed in the pentagram. These shapes also exhibit a recursively nested structure. Yet, when we observe the star-shaped pentagon, hexagon, and heptagon together, we can clearly sense that the star-shaped pentagon, or pentagram, appears more natural, balanced, and harmonious. Why is the pentagram more captivating? We need further quantitative analysis using the golden ratio to explain this. Divide a line segment into 2 parts. the ratio of the longer part to the shorter part is equal to the ratio of the entire segment to the longer part. This type of division is called the golden section, and this ratio is known as the golden ratio. We typically use the Greek letter phi to represent the golden ratio. Phi equals 1 plus the square root of 5, divided by 2, approximately 1.618. Using the shorter line from the golden section to construct a regular pentagon, and with the pentagon's sides as a base, using the longer line to form an isosceles triangle, we create a pentagram. In this pentagram, every point of intersection between lines is a point of golden section. Due to the mathematical properties of the golden section, not only is the ratio of A to B the golden ratio, but the ratio of A plus B to A is also the golden ratio. Furthermore, the ratio of 2A plus B, the side length of the pentagram, to A plus B, is also the golden ratio. The intertwining lines of the pentagram create various segments, all of which are in the golden ratio to each other. Artists have long viewed the golden ratio as the most aesthetically pleasing proportion, which makes the pentagram appear so balanced, harmonious, complete, and beautiful. Beyond the pentagram, the golden ratio often appears in the forms of the golden rectangle and golden spiral in art and nature. The golden rectangle is defined as a rectangle with length and width in the golden ratio. Many ancient structures, such as the Parthenon, incorporate the golden ratio. Many artworks, such as Da Vinci's Mona Lisa, also employ the golden ratio. If a square is cut out from a golden rectangle, the remaining part is also a golden rectangle. Cutting again leaves yet another golden rectangle, and this process can continue indefinitely. If a quarter circle is drawn within each cut square, these arcs form a golden spiral. In geometry, the golden spiral is self-similar, meaning that enlarging or reducing it maintains the same shape and overall spiral structure. In nature, the growth and arrangement of some plants and animals follow the golden spiral. In photography and painting, artists sometimes place the subject at the end of a spiral, believing it draws the viewer's eye and creates an optimal composition. The mathematical foundation of the golden rectangle and golden spiral lies in the golden ratio. The intersecting lines in a pentagram perfectly embody this ratio, making the pentagram appear more harmonious and balanced than other star-shaped polygons. This may explain why, since the time of the Pythagorean brotherhood thousands of years ago, people have been drawn to the pentagram.